Hello everyone, this is Dr. Abdul Pasha. Course name is Power System Operation and Control. In this course, the topic is numerical analysis on penalty factor. So in the earlier videos, was given information regarding the penalty factor, how it is derived and how it is relevant to the hydrothermal scheduling process and entire power system network, what it will describes and what are the basic features that we learned in the earlier case. Now we will see some simple numerical examples based on this penalty factor. So coming to penalty factor, as we know that for economic load dispatch, the incremental production cost of all operating plants should be equal. So here incremental production cost will plays a key role. So this is for same for all operating plants. It is plant 1, plant 2, plant 3, so on like that. For n number of plants, how many number of plants are there? Then the incremental production cost of all the operating plants should be same or equal. So here, but this criteria is truly only if the load and the power generating plants are localized. That means the power generated by the plant is supplies only the local loads. So suppose there are n number of power plants. There are n number of power plants supplying the local loads. That means how the load condition means load center is nearby the generating station. So if it is nearer to the generator, for example, this is generating station, it is nearest to the load center. This means there will be much more advantage with this condition. Why? Because the transmission line losses may got reduced. So the efficiency of the system may got increases here. While you are transmitting to the nearest load means the losses may got reduced, efficiency of the line may get increases. So here n number of power plants supplying the local loads means load center is nearer to the generating station. So to meet the power demand, all these n plants should be so operated that their incremental power cost is same. So this is the condition we should maintain. All the incremental power cost must be same. Then only we can operate all the plants to meeting to the load required. But this is in practical it is not possible. Why? Because the load demand will not be same for all the conditions. In some locations it may be away from the generating station. In some conditions it may be nearest, or even though the condition is existing, due to circumstances it may not ready to supply the power to the nearest load requirements. So when only it is nearer to the load case or load demand case, then only we can say that the operated their incremental power costs are similar or same. Now coming to our penalty factor analysis, in the power system network, it is a factor by which the incremental cost of power production of the plant must be multiplied to accommodate for the transmission losses. So this is the resultant of penalty factor. That means incremental cost of production of the given plant must be multiplied to accommodate the transmission losses. It is also known as a ratio of power generated by the plant to the actual power demand of the load being met after the transmission loss. Like that we may also call this penalty factor. So coming to here, incremental production cost of all operating plants should be equal or same. So here the penalty factor we may write in the equation manner as 1 by 1 minus dTL by dP for n number of units. where this dPL by dPn is the loss factor of incremental transmission loss. So for example, if you want to calculate penalty factor as in a simple manner, that incremental loss or loss factor is given dPL by dPn equals to 0.2, then this value can be substituted in the penalty factor expression. That means penalty factor equals to 1 by 1 minus incremental loss or loss factor. This can be written as 1 by 1 minus 0.2. So that gives penalty factor equals to 1 by 1 minus 0.2 means 0.8. 1 by 0.8 means it is equals to 1.25. So this is the value of penalty factor we will obtain. Next case is fuel input characteristics for two thermal plants are given here. That is F1, another one is F2. So F1 is about to 8P1 plus 0.024 P1 square plus 8 into 10 power 6 kilocalories per hour. Kilocalories per hour. F2 is 6P2 plus 0.004 P2 square plus 120 into 10 power 6 kilocalories per hour. So these are the two fuel values given, F1 and F2, where P1 and P2 are the in megawatts cases. So these are the megawatt cases. Now what we need to calculate here is plot the input output characteristics for each plant and plot the heat rate characteristics for each plant. One is plot the input output characteristics for each plant, plot the heat rate characteristics for each plant. So in the first case, if you consider input output characteristics, then consider the power in steps of 10 megawatts. Then F1 is 8P1 plus 0.024 plus 80 into 10 power 6 kilocalories per hour. And F2 is 6P1 plus 0.004 plus 120 into 10 power 6 kilocalories per hour. Now substitute the values of P1 and P2 in steps of 10 megawatts, the values of F1 and F2, which are obtained and tabulated in the next case. That means substituting this. For example, it is given with substituting for P1 and P2 as 10 megawatts. Then here 8 becomes 80. So here this table will better explains us P1, F1, P2, F2. So P1 in megawatts, F1 is into 10 power 6 kilocalories per hour, P2 also in megawatts, F2 is in 10 power 6 kilocalories per hour. So writing for all the P1 combinations starting with the 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Till 100, P1 is considered till 100. And here P2 also with same 10, 20, 30, 40, 50, 60, 70, 80, 90 till 100. And writing for F1, it is given with 162.4, 250, 342, 438, 540, 646, 758, 874, 994, 1220. So what it is indicating actually means this is the increasing order of the fuel cost in kilocalories per hour, starting with 162. So there is no other decremental seen here. All are incremental in nature. All are incremental in nature. And coming to F2 also started with 184. 256, 336, 424, 520, 624, 736, 856, 984, 1120. So like that the order follows here. So this is the increasing order of both the fuel costs F1 and F2. Now considering for the input output characteristics which are plotted here. Here on the one axis it is in kilocalories per hour, another side it is in power in megawatts. So it is started with 0, 200, 400, 600, 800, 1000, 1200, 1400. So here on another side 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Till the 100 it will be dropped. Till the 1400 we considered input output characteristics. So here calculating for heat rate characteristics, we already say that P1 is 10 megawatts at plant 1. So heat rate at this P1 is 162.4 by 10 into 10 power 6 kilocalories per hour by megawatts. And at plant 2 for P2, it is about 10 megawatts. That means heat rate is 184 by 10 into 10 power 6. So which becomes 18.4. This 184 means this becomes 18.4 division now. So into 10 power 5. Here 110 and here it will comes with the 5. So it will be kilocalories per hour, which is in megawatts. Now in a similar manner, the heat rate is computed for powers in steps of 10 megawatts. Till 100 megawatts at both the plants, the results are tabulated and curves are drawn according to the given numericals. Now coming to the output in megawatts, that also started with the 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Till 100 we have output in megawatts case. Next, heat rate into 10 power 6 at plant 1 in kilocalories per megawatt hour is 16.25, 12.48, 11.3, 10.96, 10.80, 10.77, 10.82, 10.92, 11.05, 11. That means what the changes we observed in heat rate means till here it got decreased up to 10.77 for output in megawatts up to 60. After this value, it will be 10.8 to 11.2, it will be reached. Now the same heat rate into 10 power 6 at plant 2. This is happened for plant 1. For plant 2, it will be considered with 18.4, 12.8, 11.2, 10 power 0.6, 10.4, 10.4, 10.5, 10.7, 10.93, 11.2 till it reached at 11.2 case. So that means there will be an incremental order we observed in the second plant case. So when you observe this graph, this is drawn in kilocalories per megawatt hour to the power in megawatts. So there we will observe some graphitical changes that will be observed from the topmost to the fallen case in both the extents. So they will be fold in the two levels. So like that, it may be fold on either sides of the case. Next problem is determine the saving in fuel cost in rupees per hour for the economic distribution of a total load of 225 megawatts between the two units with the incremental fuel cost. So 180 is given with the DC1 by DPG1, which is 0.075 PG1 plus 15. Another one is DC2 by DPG2, which is 0.085 PG2 plus 12. So these are the two incremental fuel costs which are given here. So with this, compare with the equal distribution of the same total load. Then what happens? Means, so total load is PG1 plus PG2. So when you add these two, then it is equivalent to the given total load, which is about 225 megawatts. This is equals to 225 megawatts. For optimal operation, DC1 by DPG1 is equals to DC2 by DPG2. Now what we need to do here is, for the given expression, DC1 by DPG1 is 0.075 PG1 plus 15. So this will be equals to this one, that is 0.085 PG2 plus 12. So now equating these two, you are going to obtain the total generating power load PG1 plus PG2 is 19.125. So this is the total sum value of PG1 plus Pg. Now solving with these expressions, and you are going to get 0.16 Pg1 is equals to 16.12. So here writing for Pg1 16.125 by 0.16, that you may get 100.78 megawatts. Now substituting the Pg1 value here, whatever you obtained 100.78 here in this place. So 0.16 into 100 into 100.78 is equal to something, this one. That means you are going to obtain Pg2 value as 225 minus 100.78. So that gives about 124.218 megawatts. This you are going to obtain. Now with equal distribution of the total load, you are going to obtain the resultant as Pg1 is 112.5 megawatts. And also Pg2 also 112.5 megawatt. That means what is given with the total load demand, that is 250 megawatts. What happens here? Pg1 plus Pg2. This is actually given in the problem 250 megawatts. So when you add these two with the obtained values 112.5, 112.5. So this is 0, 5, 2, 225. So this is now equated to whatever we solved for first one and second. So Pg1 and Pg2 we obtained 225 megawatts. Now the increase in cost for the unit 1, first unit is, that will be starts in the order of 100.78 to 112.5. That is 0.075 Pg1 plus 15, that is dPg1, which is equals to 0.0375 Pg2 square plus 15 Pg1, and the limits are applicable from 100.78 to 112.5. So when you make the Pg2 value here, Pg2 is 112.5, substitute here, you are going to multiply here 0.0375 into Pg2 square means 112.5 whole square, 15 into Pg1, that means this one 15 Pg1. But here we need to take the difference of these two. Why? Because limits are applied from 100 to 112.5. So this is subtracted from 100 and this is subtracted from 112.5 minus 100.78. So substituting for this, you are going to obtain this one 93.73656 plus 175.8. So adding these two, 93.736, 175.8. That means you are going to obtain 269. This one. That means 269.536 rupees per hour. So this is the increase in cost for unit 1. Similarly for unit 2, when the limits are considered from 124.21 to 112.5. So with this limits case, this is about 0.085 Pg2 plus 12 dPg2 equals to 0.0425 Pg2 square plus 12 Pg2, 124.218, 112.5. So these are the limits applicable. Then 0.0425. Pg2 value is about to 112.5. That we need to substitute here. It will be square minus 124.218 whole square plus 12 into 112.5 minus 124.218. So with this you are going to obtain the resultant as minus 117.889 minus 140.61. And if you subtract, both are negative signs, so they will be added, minus 117 minus 140. So this will be equivalent to this value, minus 258.505 rupees per hour. So the negative sign indicates a decrease in cost of the total load demand. Hence with this saving in fuel cost is the total value whichever obtained to 69.53 minus 258.505. So finally we obtained saving in fuel is equals to 11.03 rupees per hour. Another question is given here. Assume that fuel input in BTU per hour for units 1 and 2 are given by F1 and F2. So F1 is about 8P1 plus 0.024P1 square plus 80 into 10 power 6. Similarly, F2 is 6P2 plus 0.04P2 square plus 120 into 10 power 6. So maximum and minimum loads on the units are 100 megawatts and 10 megawatts respectively. Now find the minimum cost of generation when the following load is supplied. The cost of the fuel is 2 rupees per million BTU. So we already discussed this concept BTU. So this is the figure given. This will be started at respective time periods. So the time sequences followed here are 12, 6 a.m., 6 p.m., 12 a.m. After this, it will be started with a load of 50 megawatts, 150 megawatts. Again, it will be 50. So these are the combinations existing with the cost of fuel is at 2 rupees per million. So from the fuel input characteristics, dF1 by dP1 is 0.048 P1 plus and dF2 by dP2 is 0.08 P2 plus 6. So here the first case is given when the load is about 50 megawatts. So for economic loading conditions, we may write both will be equivalent. dF1 by dP1 is equals to dF2 by dP and equating to the total load demand, that is P1 plus P2, that is about 50. Then this P1 combination is existing with 0.048 P1 plus 8, which is equals to 0.08 P2 plus 6. So from these conditions, we have already P1 plus P2 is 50. So P1 becomes 15.625 megawatts, P2 becomes 34.375 megawatts. How we obtain means that is the sharing of the loads. That means the first P1 is less compared to the P2 case. The P2 holds for 34.375 megawatts. Therefore, F1 can be written as 210.868 million BTU per hour. Similarly, F2 is 373.5 million BTU per hour. Like that, we obtain two fuel costs about 210 and 373.5 million BTU. And when the load is about 150 megawatts, the equations can be written as 0.048 P1 plus 8 is equals to 0.08 P2 plus 6. And the total load combination is about 150. P1 plus P2 is 150. So therefore P1 is 78 megawatts, P2 is 71.87 megawatts. F1 is 851.496 million BTU per hour. F2 is 757.87 million BTU per hour. Therefore, total cost is can be written as 210.86 plus 373.5 plus 851.49 plus 757.87 into 2 into 2. So finally, the total cost becomes 52,649.61 rupees. This is the total cost incurred when the load is 150 megawatts. So 52,649.61. That total cost we obtain. Next one is on a system containing two generating plants. The incremental costs are in rupees per megawatt hour, PG1 and PG2 in megawatts. They are DC1 by dPG1 equals to 0.008 PG1 plus 8, DC2 by dP 0.012 PG2 plus 9. So the system is operating on economic dispatch. So here it is given with Pg1 equals to Pg2 equals to 500 megawatts. And dou PL by dou Pg2 is 0. So now calculate the penalty factor of plant 1. So here it is given that system operates on economic dispatch with both Pg1 Pg2 is 500 megawatts. So the condition for this optimal operation when considering the transmission loss is dC1 by dPg1 L1 equals to dC2 by dPg2 L2 equals to lambda, where lambda is the Lagrange quotient. And also given that ITL of the given plant 2 is ITL of 2 equals to dou PL by dou Pg2 is 0.2. Now the penalty factor for plant 2 is L2, that is 1 by 1 minus dou PL by dou Pg2. That is 1 by 1 minus 0.2 gives 1 by 0.8, that is about 1.25. So for optimal condition, what happened means dC1 by dPg1 L1 equals to dC2 by dPg2 L2. So both are equating here with L1 and L2. So 0.08 Pg1 plus 80 L1 equals to 0.012 Pg2 plus 9 into L2, which gives a value. Pg1 is here about 500. And substituting this with 0.012, Pg2 is also same 500 megawatts. So it is added with 9 and L2 is 1.25. L1 we need to calculate here. So when you make this combination 0.008 into 500 plus 80 into L1 means it is about to 12 L1. And here it is about to 18.75. So L1 is finally 1.562. So that is the penalty factor is about 1.5625 for this given plant. Next, a 2-bus system is already given here. This is the 2-bus system with P1 and P2. So the load is situated at bus 2. So if a load of 125 megawatts is transmitted from plant 1 to the load, the loss of 15.625 megawatts is incurred. That means we need to calculate the generation schedule and the load demand. The cost of received power is 24 rupees per megawatt. Solve the problem using coordination equations and the penalty factor method approach. The incremental production costs of the plants are given. dF1 by dP1 is equals to 0.025 P1 plus 15. dF2 by dP2 equals to 0.05 P2 plus 20. These are the two incremental costs which are given as a dF1 by dP1 and a dF2 by dP2. So here 2-bus system contains load P1 and load P2. That means at second bus the load is connected here. Two generators with powers P1 and P2. This is generator 1. This is generator 2. Powers are P1 and P2. These are the two powers. So since the load is at bus 2 alone, the losses in the line will not be affected by the generator of plant 2. What happens here means load is at bus 2. So therefore losses in the line will not be affected by the generator of the plant. So here the loss coefficient can be calculated with the condition PL, that is B11 P1 square plus B12, that is B12 as B21, which is equals to 0, and B22 equals to 0. Then it becomes 15.625 equals to B11 into 125 square. So this may be written as 0.001. This is one of the loss coefficient called as B11. Also we know that these loss coefficients can also be called as transmission loss coefficients or B coefficients. Like that we may call this combination. Now coordination equation is dF1 by dP1 plus lambda dou PL by dou P1 is given with the combination called lambda. Here PL equals to 0.001 P1 square or we may rate this PL as dou PL by dou P, that is 0.002 PL. Substituting in the coordination equation for plant 1, we will get 0.025 P1 plus 15 plus lambda 0.002 P1, which is equals to lambda case. So here 0.0025 P1 plus 0.0048 P1 plus 15 equals to 20. Now we can write this combination here as 0.073 P1 is equals to 9. So writing for P1 it becomes 9 by 0.073. So this will be cross multiplied and you may get 123.28 megawatts. So and from the coordination equation for plant 2, for the given plant 2, we may write 0.05 P2 plus 20 equals to 24 or P2, that is about 80 megawatts. So with this, the transmission loss is PL and it is about 0.001 into, here it is a P1 square, that means 123.28 whole square, that is 15.19 megawatts. So load equals to PD, that is 123.28 plus 80 minus 15.1. So this is about 188.1 megawatts. This is the load PD. So the solution using penalty factor as follows here. So penalty factor for plant 1 is 1 by 1 minus dou PL by dou P1. That is 1 by 1 minus 0.002 P1. So where this 0.002 is dou PL by dou P1. And writing for this one, dF1 by dP1 into 1 by 1 minus 0.002 P1 gives a value of 20. So 0.025 P1 plus 15 by 1 minus 0.002 P1 gives a value about 20. So with this condition, simplifying for it, cross multiplying and getting P1 as 123.28 megawatts. Similarly, since dPL by dP2 is 0, then L2 is unity. So the incremental cost of received power equals to the incremental cost of the production case. That is 0.05 P2 plus 20 equals to 24. Or we may write P2 as 80 megawatts. So what happens here? We got the value of P2 and we got the value of P1. So this total combination gives 123.28 plus 80 megawatts. So this is about totally 200 above P1 plus P2 combination. So these are some of the references I have gone through this electrical for you. freevideos.com, ustudy.in, and free engineering textbooks. So like that we can solve so many examples based on penalty factor, which gives us suitable solutions in solving the penalty factor. So only the condition holds good for penalty factor is 1 by 1 minus dou PL by dou P1. So here dou PL by dou P1 itself gives the penalty factor, whatever it may be the condition. So the resultant may be the penalty factor for the given power system network with any number of buses it is given. So that is the numerical analysis for penalty factor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.